Hello, my darlings. All right, so we're back for some more U substitution. This time we're going to be looking at arc trig functions. So remember when we had tan inverse of an angle, if we took the derivative of that, it was 1 over 1 plus the angle squared times the derivative of the angle. Well, that can be adjusted a little bit so that it doesn't have to be a 1 plus. It can be any constant. Because if you have an angle, say x over a, that would be 1 plus x squared over a squared. But if we multiply top and bottom by a, we would have something that looks like this. So if we take the integral of 1 over a squared plus x squared dx, that's the tan inverse of x over a, but we have to divide by the a because we didn't have the a in the denominator, and then plus c. Similarly, we can do something with arcsine. So the integral of 1 over the square root of a squared minus x squared dx is sine inverse of x over a. All right, so here's how this works. Let's say we have an example here. So this is the integral of dx over 9 plus x squared. If we look at this, a squared is 9, which means a is 3. That's in the form 1 over a squared plus x squared. So that tells me this is a tan inverse, an arctan of x over the a is 3. Don't forget to divide out by the a plus c. There we go, done. Now we can do one similar for sine inverse. If we look at this, the 16 is our a squared, which means that a is 4. So this means that the integral of dx over the square root of 16 minus x squared is sine inverse of x over 4 plus c. Ta-da! Now, they're not always going to be that straightforward. You knew that, right? Now, there's different ways to do this. Let's look at one way first. This gives us the integral of dx over 9 plus 3x squared. The problem is we don't want a 3x squared. We want just x squared. Well, how could we do that? We would need to factor a 3 out of the bottom, which would leave us with 3 plus x squared, right? So now we'd have 1/3 times the integral of 1 over 3 plus x squared dx. So now, if that 3 is our a squared, a is radical 3. So we keep our constant 1/3. This is in the form for tan inverse, so it's tan inverse of x over the a is radical 3. Don't forget to multiply by 1 over the a, so 1 over rad 3, and plus c. So I could simplify that to 1 over 3 rad 3 tan inverse of x over radical 3 plus c. Ta-da! There you go. Let's try another one. Again, we have an integral of dx over 16 times 1 plus 1/4 x squared. We could distribute the 16, but then that still won't give us an x squared. We want that to be x squared, right? And we have 1/4, so we need to multiply by 4. Well, there is a 4 hiding inside a 16, right? 16 is 4 times 4. So if we pull out one of the 4's as a 1/4, because it's in the denominator, times the integral of, that leaves us with another 4 times this 1 plus 1/4 x squared dx. And if we multiply that 4 through, we have in the denominator 4 plus x squared. Now the 4 is our a squared, so a is 2. Now I keep the 1/4. This is in the tan inverse form, so it's tan inverse of x over the denominator is a, which is 2. Don't forget to multiply by 1 over a and add c. So 1/4 times 1/2 is 1/8 tan inverse x over 2 plus c. Ta-da! Now, there are other ways to do that besides trying to make those 4x squareds and 3x squareds and 1/4 x squareds into x squareds. Okay, we can do a U substitution. especially when you're looking at the sign, you don't want to have to factor out a square root of 4 because that's going to be a pain in the neck, okay? You don't want to have to factor out under the radicals. So if you look at this, we have these forms with u's. The integral of du over a squared plus u squared is 1 over a tan inverse of u over a plus c. Same rules we just had, we just changed all the x's to u's, okay? Which means if I look at this example 2, the integral of 5 over the square root of 1 minus 4x squared, my a squared is 1, my u squared is 4x squared. That means a is 1 and u is 2x, right? So if I do my u substitution, I have the integral of 5 over the square root of 1 minus u squared. And I've got to do my du dx here, so hold that thought. If u is 2x, then du dx is 2. So I have du equals 2 dx, and du over 2 equals dx. So now we're going to multiply up here by du over 2. Well, I've got a constant now of 5/2 times the integral of 1 over the square root of 1 minus u squared du. So I'm going to keep my 5/2. This is my form for sine inverse. And sine inverse is u over the a is 1 plus c. So this is 5/2 sine inverse. And my u, remember, is 2x. I don't need to divide by 1 plus c. And there we are. Okay? Now, if u is any differentiable function, now here's a new one, the integral of tan u du. We've never taken a derivative of something and gotten tan u as the answer, nor have we ever taken the derivative of something and gotten cotan of u as an answer. Well, it turns out that the integral of tan u du is the negation of the natural log of the absolute value of cosine u plus c. Or it's also the same as the natural log of the absolute value of secant u plus c. Interesting, right? How does that work? Well, let's take a look. We've got the integral of tan u du. Now, tangent, remember, is sine over cosine. So sine u over cosine u du. Now, we want to do a u substitution, but the problem is we already have u's, so we're going to pick a different letter. I'm just going to pick v. You can pick whatever letter you want. I'm going to choose the denominator, cosine u, because it's the denominator. Okay, I don't have anything raised to a power, so I'm going to let my denominator be what I'm substituting for. So my v is cosine u, which means my derivative dv du, because I'm taking the derivative of v with respect to u. The derivative of cosine is negative sine u. Now I'm going to multiply by du, and then I'm going to divide, so I have dv over negative sine u equals du. Now I'm going to come back and I'm going to try to substitute and simplify in this integrand. So I have the integral of sine u over, now wait a minute, my cosine u is my v, times my du is dv over negative sine u. Okay, so my sine u's cancel, but there's a negative. They actually divide to -1. So it's going to be the negation of the integral of 1 over v dv. Well, that's the negation, and I know that the antiderivative of 1 over v is the natural log of the absolute value of v plus c, equals the negation of the natural log of the absolute value. But what was our v? That was cosine u. So here's the rule that we had found, okay? But how did they get that second one? Do you remember what the natural log of 1 is equal to? E to the what exponent is 1? 0, right? So I'm going to say the natural log of 1 minus the natural log. So all I've done is put a natural log of 1 up front. I haven't changed anything because the natural log of 1 is 0. But when there's subtraction, that used to mean there was division. So it was 1 divided by the cosine of u. And 1 over cosine u is secant u plus c. So that's how it is also equivalent to this. You could prove that the integral of cotan u du is the natural log of the absolute value of sine u by doing the same type of procedure. I'm not going to do that with you here now, but it's the same thing, only it's the integral of cosine u over sine u, and you go from there. This is more fun, and I would not leave this one to you on your own, because I'm going to do this neat little trick that you would never think to do on your own, and that's okay. The integral of secant x, I am not going to change that to 1 over cosine x, because if I do that, I have 1 over cosine x. My u could be cosine x, but my du dx would be negative sine x, and I don't have a negative sine x. I cannot wind up with a 1 over u times a du over negative sine x. I cannot integrate with a u and an x. That does not work. So I can't do a u substitution that way. So I'm going to try a whole different technique. I'm going to integrate secant x, and I'm going to multiply by 1. But my 1 is going to look like secant x plus tan x over secant x plus tan x, right? That's 1. I do not expect you at this point to have thought of that on your own, so please don't panic, okay? This is a new technique for you. I'm multiplying by 1, but I'm using a weird trig identity. All right, now I'm going to distribute in the numerator. So secant times secant is secant squared x, plus secant times tan is secant x tan x, and that's all over the denominator, secant x plus tan x dx. Now I'm going to do a u substitution. I'm going to let my denominator be u. Secant x plus tan x is my denominator, and that's my u. Now let's find du dx. The derivative of u is du dx equals the derivative of secant x is secant x tan x plus the derivative of tan x is secant squared x. Now we're going to solve for dx. So first we multiply, then we divide. So now we know dx. Now we're going to do the substitution. So I have this integral. My numerator is secant squared x plus secant x tan x all over. That denominator is my u. My dx is du over secant x tan x plus secant squared x. Now notice the denominator of that fraction and the numerator of the first fraction are the same. They're reversed around addition, but addition is commutative. So they divide out to 1, which means all I have is the integral of 1 over u du. I know the antiderivative of 1 over u. That's the natural log of the absolute value of u plus c. Well, that's the natural log of the absolute value. What was my u? Secant x plus tan x plus c. Wow. So we just proved that the integral of secant u du is the natural log of the absolute value of secant u plus tan u plus c. And the integral of cosecant u, du, very similarly, is the negation of the natural log of cosecant u plus cotan u plus c. All right, guys. So we've done a bunch of new antiderivatives with arc trig functions and then a couple of new ones. All right, guys. Have a wonderful day. Bye.